All right. Yeah, the bonus, if you have it, you can turn that in. Anyone? Anyone?
I did part of it, but I finished it.
Anything's better than nothing. Yeah, I guess so. I just don't know when you'll get your homework back. All right. What's that? Okay.
Yeah, yep. This is part A.
Oh yeah, that one. I forgot about that one. That was that Bessel one, yeah. Okay. Looks like math. Okay, last class I handed out the notes, remember? And I had some problems with the copier, and so I only had a certain number of color copies. Well, I went to the copier yesterday, and they were sitting there. So anyone want color copies of last class's notes? Here, take two. Take two. Anyone else? Anyone else? You want? Yeah. All right, we are going to cover now today's notes, Taylor series. I printed these out for you too. What? Sorry?
Like part of the other notes we did?
What part?
Oh.
Yeah, that's the same thing we did last class, but in color.
Okay. And it's just larger.
Does it look a little different?
It looks thicker than this note.
Oh, it may not have did it print front and back or no?
Print it all the way up to ARC 10.
Okay. Well, here's today's though. Today's notes. Today's notes. Today's. So we're coming down to the end here. I'm trying to get as far as I can by next Tuesday. My plan is to have very little discussion about the final until, like, you know, I don't know. Tuesday I'll talk about the final, because really we're going to spend time continuing on. But you can imagine your finals are going to be mostly Chapter 8, and then it's going to be what we do in Chapter 9. But let's talk Tuesday. Let's get right down to this. We are going to talk about Taylor and Maclaurin series. It's the last section that we're going to do in Chapter 8. So we've come to kind of the end, and there's a lot here. I didn't want to write all this on the board. Let's see if you can follow this. Suppose, that's what that symbol means, remember? That capital S with the little line on it, that little thing right there. That's suppose. Suppose a function is represented as a power series. That's what that first line says. Suppose we have a power series representation of a function here, right? Then we can just plug in n equals 0, n equals 1, 2, 3, 4, and we get equation 1, right? That's what that's what happens if you just plug in your various values of n. That's all right? We wish to determine what those constants in front of our power series turn out to be, okay, what they are. So what we're going to do first is this. We're going to let x be equal to a, right? So look at this equation, let x be equal to a in here, and doesn't take everything and turn them into zeros except for that first constant, right? Everything else 0, 0, 0, 0, 0, 0, 0. So all we get is when we plug in x is a, we get that f of a equals that constant and then zeros. That means that that constant is equal to the function's value at a. Yes? Okay. What? The what? Oh, I think it's working. Oh, thank you for reminding me, but hello? It looks like it's there. Okay. All All right, so we actually know what C sub 0 is now, right? It's f of a. Now, how are we going to find the next constant? So what we do is we take the original problem, right, and we differentiate it. Take the original equation 1. Take equation 1 and differentiate it. So what is the derivative of a constant? 0. What's the derivative of a constant times x minus a? Yeah, that's just a 1, right? So C1. So that's where we get C1 right there. Then the derivative of C2 x minus a squared, 2 comes down. Then subtract 1, so it's just that to the first power. So here's our 2, C comes down, x minus a to the first power. And then we keep doing it, right? Do it. And so we get a 3, C3, blah, blah, blah. And now we get what we're going to call equation 2. Here it is. Now we're going to do the same exact thing. We're going to plug in x equals a and see what happens. So plug in x equals a. Everything dies, right? Everything dies in this except for C1. So that means that C1 has to be the derivative of the function at a. Y'all follow that? I forgot to put dot, dot, dot here, but there should be there. Now we do it again. We differentiate again. So when we differentiate, we take the derivative of equation 2 and create equation 3. So how do I say second derivative? I could do prime prime, or you could put a 2 in parentheses. Has to be in parentheses, though. That means your second derivative. So the second derivative of f is the derivative of C1, which is 0. Then derivative of this, which is just 2C2. 2C2, that sounds like a dance or something. Okay, this one right here, 3C3 times this, the 2 comes down, and now you have 2 times 3, C3, x minus a. And then you keep going, right? The 3 comes down, 3 times 4, C4, x minus a squared. Repeat the process. X is a again. That means the second derivative at a equals 2 times C2, right? It was 2C2. Divide both sides by 2, and you get that. So C2 is the second derivative of the function evaluated at a divided by 2. Y'all see how this is working? We continue. We repeat. Now differentiate equation 3. So this time, and since you've got it in front of you, look at equation 3, take the derivative. The derivative of 2C2 is gone, right? What's the derivative of 2 times 3C3? X minus a. 2 times 3C3. And then over here, what happens? This one right here? 2 comes out, so now you have 2 times 3 times 4, C4 x minus a to the first power. And we start to create a pattern. Here's our derivative of our equation 4. We plug a in again to this. This is the third derivative. The third derivative at a gives us 2 times 3, C3. Divide both sides by 2 times 3, and we get C3. And I keep going. I do it again, take derivative again, and now I get the C4. So what we get is a general formula for it. We know that each of the C sub n's is just the nth derivative, right? The nth derivative at a over n factorial. Oh, this is a 4. Does that look like a 4 or an n on your paper? Looks like an n. Let's fix that. Should be a 4, right? Right there. The fourth derivative. So do you see the pattern has been created? All right. Yes. I think I say it here in a second, or maybe I said it before. Hold on. I know it's on here. Yeah, if you go down a little bit more, where it says theorem, you'll see. Okay, so what we have, do you need notes? Anyone else come in? I didn't realize. So we have this formula. That's pretty incredible because what it does is it allows us to come up with a formula for our function, right? Where we know what each of the constants in front are going to be, and all we need to know is there's a couple things. We need to know the function's value at a single point. And we need to know what all the derivatives of the function are, which seems like that could be a problem sometimes. But a lot of times we can find derivatives and then take derivative again, second, third, fourth, fifth, sixth, so it's not that big of a deal. But it's a way to come up with the constants, which is really nice. So here's the theorem that we have. We have what's called the Taylor series of a function f at a. We also say sometimes it's a Taylor series centered at a, or we say it's the Taylor series about a. Those are all the same if you hear someone say that or you see a book refer to it. Here's what the theorem says. If f has a power series expansion, if it does, in other words, if you can define a function as an infinite series with some radius of convergence, right, then the coefficients will always be this. And therefore, your function, instead of having that c sub n right here, is now that formula. And that is called the Taylor series expansion of f about x, or f centered at x, or f at x. I said x, a. Centered at a, about a, at a. And this is where I was pointing out. Notice that when you plug in 0, 0 means the 0th derivative, which means no derivative, which means the function itself. Okay, so if I plug in 0, it's the 0th derivative, which just means f of a, divided by 0 factorial, but 0 factorial, remember, was 1. So I'm just pointing that out. For n equals 0, it's a little weird. Any questions? It's just a formula. Now, we do have a more specific, more narrowed down version of this formula. This formula is very general because a can be any number, as long as it's within the radius of convergence, right? But if a is 0, okay, then we don't call it the Taylor series anymore, we call it the Maclaurin series. So a Maclaurin series is a Taylor series centered at 0. That's all it is. So what happens is that becomes a 0, right? So it's always the function adds 0, the derivative adds 0, second derivative adds 0, third derivative adds 0, and then the x minus a just becomes x minus 0, so that's just x. Maclaurin. Have any of y'all ever watched Good Will Hunting? Ever seen Good Will Hunting? Yeah. There's that part where Matt Damon burns his paper. Remember, the professor. In that scene, he's going over Matt Damon's work, and he's looking at it. He's like, oh, and he goes, I see you use Maclaurin here. If you pay attention to it, he's referring to Maclaurin series. Just FYI, every time I say Maclaurin, I think about that scene in that movie for some reason. So Maclaurin is a power series, a Taylor series centered at 0. Now, I worked through on paper how we find a Maclaurin series for sine x. All right, so because it's written down, I'm not going to write it down. I'm just going to walk through this. So here are the instructions. Find the Maclaurin series for f of x equals sine x. So the first thing I did was I said, I'm going to need all the derivatives of sine, and I'm going to need them at 0, right? That's Maclaurin. You take the derivatives, evaluate at 0. So first, the 0th derivative is just sine, isn't it? And then what is the 0th derivative at 0? Sine of 0 is 0. Okay? Then I need the first derivative of the function. First derivative of sine is cosine. Now I plug in 0 into that. Cosine of 0 is 1. Again, second derivative. What's second derivative of sine? Well, that's derivative of cosine, which is negative sine, right? Plug in 0, negative sine of 0 is 0. Third derivative. Third derivative of sine is the derivative of this one, so it's negative cosine. Again, plug in 0. Negative cosine 0 is negative 1. What's wrong? Derivative sine's cosine. Derivative of cosine is negative sine. They just keep on alternating. Well, it alternates, but it takes 4 to alternate, doesn't it? It goes 0, 1, 0, negative 1. Then it's going to go what? 0, 1, 0, negative 1 again. It starts to cycle, but it takes 4 to cycle, doesn't it? Agreed? So I did the fifth, 6th, and 7th here without showing the work. And just to show the pattern that what you get at 0 is the same thing you get at 5. What you get at 1 is the same thing you get at 6. What you get at 2 is the same thing you get at 7. What you get at 3 would be the same thing you get at, let's see, hold on. 1, 2. What happened to my lines there? Oh, yeah, this one goes here. So this is I said that wrong. What you get at 0, you get at 4. 1, you get at 5. 2, you get at 6. 3, you get at 7. Yes? Okay. So let's look at now the Maclaurin series for sine. Here's the formula for Maclaurin series, right? That's it right there. So we found, I just wrote them out. Just plug in 0, plug in 1, plug in 2, plug in 3, plug in 4, right? Now what did we say the 0th derivative at 0 was? You have to go back up and look. It was 0, wasn't it? Over 0 factorial is 1. X to the 0 is 1. Okay? Then you plug in the first derivative at 0, which was what? 1 over 1 factorial, which is 1, and then x to the 1 is x. Following? Then you do second derivative at 0, which was what? 0 over 2 factorial, x squared. Then the third, and then the fourth, and you keep going, right? Now, everywhere we have zeros, they go away, right? This one goes away, this one, and this. All the even powers go away, don't they? So what you're left with is the x, the negative 1 over 3 factorial x cubed, plus x to the 5th over 5 factorial minus x to the 7th, and you could keep going. Do y'all see that or not? Now we go from here and we convert it back to a power series. First of all, it's alternating, isn't it? Positive, negative, positive, negative. So I have negative 1 to the n, right? That should get me alternating starting at 0. So I plug in 0, I'm going to get a positive. Plug in 1, I'm going to get negative, so that's going to alternate. X to the 2n plus 3 comes from the fact that I realized that all these powers are odd numbers, right? 1, 3, 5, 7, starting at 1, right? Which means that when I plug in 0, I need 1. When I plug in 1, 0, I need 1. When I plug in 1, I need 3. When I plug in 2, I need 5. So 2n plus 1 will create these odds, won't they? But in the denominator, I need the same thing. I need 1, 3, 5, 7 factorials. So the formula down here is 2n plus 1 again, factorial. Y'all see how that works? Okay, now, this is the Maclaurin series for sine. This is it right here. Or this, if you write it out. Now, how many of you remember learning at some point in time that sine is an odd function and cosine is an even function, right? Take a look at this series. Tell me about the powers on all those x's. They're all odd. That's why it's an odd function. And then when we do cosine, when you do the Maclaurin for cosine, you're going to find out that every power is even. All right, now I continue on with this because now what we have is a power series, right, where we know what the constants are, right? Don't we know the constant in front, right here? And so what we could do is talk about the radius of convergence. So I'd like to know, when does this Maclaurin series converge? So we do ratio test. So I go through this whole ratio test. Let's talk about this ratio test here. Remember, you have to, ratio test is a sub n plus 1 over a sub n, absolute value. So I do it all here. And I'll leave it to you as an exercise to verify this. What you get at the end is this, right here. And because as n goes to infinity, this goes to 0, it doesn't matter what x is. And so it converges for all x. It's less than 1, right, for all x. So it always converges, which means the radius of convergence is infinity. That means I can use this power series to approximate the sine function always. It's for any x. Okay? For any x, I can use this. Now, a true Taylor series goes from n equals 0 to infinity, all right? True Taylor, it's infinite series. But we can get what's called the nth degree Taylor polynomial, which is basically an approximation. You know how I've been talking about with series, we can go as far as we need to go to get as close as we need to get? All this says is, look, if we take this, forget this right here. If we take this right here and we started at 0 and ended at n, so instead of going from n to infinity, I'm going from I to n. And then that's the Taylor formula right there, right? That's what we got. We found that formula for the C sub n's. This is just a finite series. So I'm going out and at some point stopping. We call that the nth degree Taylor polynomial. Because if we stop somewhere, isn't it just a polynomial? A finite polynomial. And that would be our approximation. Since the original function is the infinite series, and I'm rewriting that going from 0 to n and stopping, and that means that I must have some remainder, right? In other words, the true function has more terms that I stop, so there's an infinite more towards that keep going. That infinite number of terms at the end is called the remainder of the nth degree Taylor polynomial. And here's a formula for the remainder. Now, we're not going to get into this in depth at all. I'm just showing it to you. The thing is, there are ways that we can get a bound on that remainder. We're not going to do it in here, all right, because we just don't have time. But there's a way to know how big that remainder could possibly be. So we can know how much error we have. If we approximate it with this, and we know that this remainder can only be plus 1/1,000,000th, then we know we're within 1/1,000,000th of the exact answer. So a lot of times in physics and stuff, this is really what we're interested in. How far do we go out to make sure that we're far enough to get the accuracy we desire? All right, so talk about a little more there. So here are some examples. Find the Maclaurin series for each of these. So this is all examples now. Ready? Now I did these last time in my previous class, so thinking of maybe doing something a little different for Maclaurin series. Okay. Do y'all mind if I change those examples? So what's something I could do that would be Y'all want to do cosine? Let's do cosine. I want us to find Maclaurin series for this. See, when I say Maclaurin series, I've told you right now x is 0. So there's only one formula for this. So the formula is this. What is it? F of x equals sum n equals 0 to infinity f nth derivative of f at 0 over factorial x to the n. So x minus a, but a is 0. So that is the Maclaurin series for any function. What I need to know are what are all those derivatives. So let's start taking derivatives, all right? The 0th derivative of the function is what? Cosine x, right? The 0th derivative. Now, let's plug 0 into the 0th derivative. So what is cosine of 0? 1. Everyone see how I'm doing this? Now you take the first derivative. What is the first derivative of cosine? Negative sine x. Now plug in 0 into that, and you get negative sine of 0, 0. Now take the second derivative, which is negative cosine x. Now plug in 0. So negative cosine of 0 is negative 1. If I go one more time, I should get 0, and then it should start cycling, right? Now, sine and cosine are nice because they cycle, but not every function you ever do is going to cycle. So let me go f third derivative x equals derivative, that's what? Sine x, right? So the third derivative at 0 is sine 0, which is 0. And then the pattern repeats, right? So the fourth derivative is going to give us what? 1, and then the next one, 0, negative 1, 0, dot, dot, dot. So that's our pattern. So what I'd like to do now is go back to that formula that I had. F of x will be equal to sum n equals 0 to infinity f, the nth derivative of f at 0, all over n factorial x to the n. And let's start writing this out. Let's first let n be 0. Now, do you want me to write down like f 0th derivative at 0? Can I go straight to the number? Straight to the number? Like, do you want me to write this down? F 0, 0, 0 factorial x to the 0. You want me to write a few of those out, and then the next line we'll plug everything in? Okay. Plus, now f, I'm replacing n with 1. 1, first derivative at 0, 1 factorial x to the 1. Then second derivative at 0 over 2 factorial x squared plus da 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 da. Well, should we go a few more? No, that's all right. On the next line, I'll write a few more. I'll put the numbers in. I'll go further with my numbers, but I'm going to stop writing that. What was the 0th derivative at 0? What was the 0th derivative at 0? It was 1, wasn't it? So that's going to be 1 over 0 factorial, which is 1, x to the 0, which is 1, plus what was the first derivative at 0? 0 over 1 factorial x to the 1 plus, what was the second derivative at 0? Negative 1 over 2 factorial x squared. Okay, now it would start repeating, right? So I would have, right, is it going to repeat now? No, I'm going to have 0, right? 0, my next one. So 0 over 3 factorial x cubed. Now it repeats. So I'll do it in blue just to show you it's going to start repeating. Now it's what? 1 over, where am I though? 4 factorial x to the 4th plus 0 over 5 factorial x to the 5th plus negative 1 over 6 factorial x to the 6th. And then the next one will be a 0, won't it? 0 over 7 factorial. Keep going. All right. Let me try and give myself a little more room here. See if I can move this up. Okay. Let's start killing the things off that are gone. All the 0 terms are gone, right? All that's left are even powers. And so we get, what, 1 plus, well, actually, we're going to write minus 1 over 2. I'm going to leave it as 2 factorial, even though 2 factorial is 2. I'm going to leave it. Then we have plus 1 over 4 factorial x to the 4th. What would the next one be? Plus, or minus 1 over 6 factorial x to the 6th. Okay, what would the next one be? Plus 1 over 8 factorial x to the 8th. So what we need to do now is come up with a formula. A new sigma notation for this. So tell me about the powers on the x's. Well, okay, it's alternating. You want to take care of that first? Alternating starting with positive, right? Okay, so I'm going to do negative 1 to the n plus 1, or n minus 1 would work. Oh, wait, no, hold on. It's starting at, sorry. There we go. Right, and since we're starting at 0, that'll give us 1, then the next one will be negative. And okay, now we need, I'm going to look at the powers of x. We have even powers, 2, 4, 6, but we start at x to the 0, right? So it's even starting at 0. So x to the just 2n. That'll work, won't it? If n is 0, we get 0. If n is 1, we get 2. If n is 2, we get 4. If n is 3, we get 6. So that should work. And then what about our factorials? 2n factorial. 2n in parentheses factorial. That is not the same as 2n factorial, right? Those are two different things. 2n in parentheses factorial is different than 2n factorial. Convince yourself. Let n be 3. What would that be over there? 2 times 3 times 2 times 1, right? What would this be? 2 times 3, 6. 6 times 5 times 4 times 3. Yeah, there the factorial. Here the factorial is just on the n. On the other one, it's on everything inside. Totally different things. What would what? Yeah, if I plugged in 3, it'd be 2 times 3 times 2 times 1. That would be your 3 factorial. Where the other one would be 6 factorial, and they aren't the same. No. No. All right, that's it. That's the formula. All right, now let's try something a little different. All right. Let's do a Taylor series. Maclaurins are pretty clean. Did anyone have a question on this formula, though? Anyone have a question on this formula? Oh, we didn't get radius of convergence. I'll let you do that on your own. It's infinity. It's all real numbers. Same thing. Ratio test. Okay. And it'll go to infinity. It'll go to 0. It'll be less than 1 always. So negative infinity to infinity. All right. New problem. Let's find you want Taylor? Yeah, let's do Taylor series for f of x equals 1 over x at a equals -3. Let's first start by getting the formula for a Taylor series. So f of x the nth derivative at a over n factorial x minus a to the n. So now we actually have an a. We're given an a, aren't we? Maclaurin, a is always 0, right? Okay, so let me finish this off. Now that I know what a is, it's given to me in the problem, -3. What this really is this. It's the sum, n equals 0 to infinity, of the nth derivative of f at -3 over n factorial x plus 3 to the n. X plus 3 because minus the negative becomes plus. Yes? Well, we need the derivatives. That n up there, that's the nth derivative. So every term, first term is the 0th derivative, second is the first, then second, then third, then fourth, then fifth, then sixth. We need to find a list of derivatives now. Okay, let's look at it. So I'm doing some work here. What is the 0th derivative of the function f? It's 1 over x, which is the same as x to the -1, isn't it? I'm going to keep that in mind because I'm going to take derivative of that in a second. Now let's plug what into this? -3. If you take the 0th derivative and you plug in -3, you get -1/3. Right? All I'm doing is plugging -3 in right here. So it just becomes -1/3. Now, first derivative of that function is -x to the -2, which is the same as -1 over x squared. So if I take the first derivative and I plug in -3, I get -1 over 9. -1/9? Pardon? The negative is from this right here. I put -3 squared, I get +9, but then the negative on top. And now second derivative equals what? So 2x to the -3, which is the same as 2 over x cubed, which is, now plug in -3. It's negative 1 over 27? No, 2 over 27. It's not negative? It will be negative because you're cubing the negative 3, right? So negative 3 cubed here. Are y'all seeing this? What you're going to notice is that this is the first time we don't have the cyclical nature like we had in sine. But there is a pattern that's being created here. So let's keep going and see if we can get our heads around this pattern. Yeah, every derivative we take, what's happening to the denominator? It's going up by a power, right? Okay. Let's do our third derivative. And now we get what? 6, right? Is it okay if I write it like this? Negative 2 times 3x to the negative 4. I'm trying to get you to see that we're almost getting factorial out front, aren't we? Every time we move through here. Because the next time we take a derivative, we're going to have 2 times 3 times 4. The next time we're going to have 2 times 3 times 4 times 5. Do you see? Okay. So this is really negative 2 times 3 over x to the 4th. Now we plug in third derivative at negative 3 is where? 81. Now I'm going to start writing it like this now. 3 to the 4th. Doesn't matter. It doesn't matter that it was negative, right? Because when I do it, it's going to be positive. And the previous one was what? This one was 3 to the 3rd, and this one was 3 squared. What does it appear is happening no matter what we do? It's the denominator keeps going up by a power of 1, right? 1 integer. Power goes up by 1. The numerator, well, all of them are negative, right? Every single time we do this, it's negative still. And the numerator is like, this is 3 factorial. This one was 1 factorial, and that one was 0 factorial. Wasn't it? Is that enough for you to get the pattern? Let's see. If you're trying to get this as a pattern, your C sub n's are equal to, oh wait, no, hold on, we got to put those over n factorial. Hold tight. Write down what the next one would be. Let's just write it down. What the heck? It would be negative 2 times 3 times 4 over 3 to the 5th. Well, so far, none of them have been positive. Try it. Try it. Look, negative 4 comes down and becomes positive, right? But then it's to the negative 5, which means that that's going to be 5th power. Negative 3 to the 5th power is negative. The negative 4, if we take the next derivative, it'll be negative 2 times, well, I should say positive. It'll be 2 times 3 times 4, but then x to the negative 5, which is 2 times 3 times 4 over x to the 5th. When we plug negative 3 into x to the 5th, we get our negative. So by all indications, it's staying negative all the time. Okay, you ready to start writing this stuff out? We can go back to the Taylor series now. So our Taylor series, as we said before, should be sum n equals 0 to infinity, nth derivative at negative 3 over n factorial, and then x minus a to the n. But we just discovered that this numerator here, right, this has a pattern to it. The pattern is that it's off of everything we just did, right? The fn negative 3 looks like it's equal to, what did everyone say? Negative n, well, where are we starting our n? It's 0, right? So n factorial over 3 to the n plus 1. Do you all buy that? We all agree on that? This part right here. Yeah, go ahead. What? No. It's just a negative 1 times the n factorial. Do you all agree that that's what that should be? If we start at 0, right? 0 factorial is 1 over 3. So we get the first one. We let n be 1. We have 1 factorial. So negative 1 over 3 squared. And then 2 factorial. And then, yeah, that looks right. Now we're going to divide all that by what? N factorial, which is going to cancel the n factorials. So we have this equals sum n equals 0 to infinity. What? Negative 1, be careful, that negative 1's still there. 3 to the n plus 1. Then x plus 3 to the n. No, because you can't. You can't, no. This is it, though. This is our power series right here. So we didn't have to write them out term by term and then look for a pattern and go backwards. We kind of got it without having to write anything down like we did in the last problem. All right. I need to find radius of convergence. Are there any questions, though, up to this point? This is our Taylor series about x equals, what was it? Negative 3? Okay. Yes, this yellow highlighted stuff was replaced there. So the n factorials canceled, right? This n factorial here canceled with that n factorial there. I was just left with the negative 1 over 3 to the n plus 1. Okay? All right, let's take this and go ahead and find its radius of convergence. I don't know. I haven't done this problem before, so I'm not sure what it's going to do. So I'm going to have to check it. And so are you. So now we're going to do ratio test. Limit n goes to infinity. Absolute value. It'll be, how can I write this? How about x plus 3 to the n times x plus 3 over, and then a negative, right? The negative 1 is gone. Absolute value is going to kill it off anyway. 3 to the n plus 2, which is really 3 to the n times 3 squared. This right here is a sub n plus 1. Isn't it? Times the reciprocal of a sub n, which would be 3 to the n times 3 over x plus 3 to the n. That's your a sub, and, well, the reciprocal of it. So you see that? I mean, I really hope you've done enough ratio tests now that you're okay with that. And now you should get cancellation here. 3 of the n's are gone. Yeah, take off the power here, cancel with one of those. So, yeah, pretty good. Limit n goes to infinity. The only thing left in here is a 1/3 and an x plus 3, right? I need that. Oh, and I let n go to infinity, right? There is no n. Right? There is no n. So that's my answer. It's 1/3 absolute value of x plus 3. Now, ratio test says I need that to be less than 1, right? So I need 1/3 absolute value of x plus 3 to be less than 1 for this to converge. So absolute value of x plus 3 must be less than 3. So your radius of convergence is 3. And the interval of convergence so subtract 3, -6 to 0. And then you could check endpoints and all that stuff if need be. What this says, though, and this is pretty important, is that the series we found is our answer, right? Which is right here. This series can be used to approximate that function as long as we are looking between -6 and 0. Okay? So if I want to look at that function, 1 over x, and I want to look at it between -6 and 0, I can use the series we found to approximate it. Now, what if I want to get somewhere else? What if I don't want to, like, I guess what I need you to get your head around is that right now, if I try and find f of -2, I can just plug -2 into that series, right? And it will converge to a number, and that'll be my answer. Yes? But what if I want to know what f of 2 is? Yeah, I can't use that series. What I would need to do is shift it. And to shift it, I would need to change the a. You know how we did the a about -3? I would move the a, change the a, so that I can move it over and get the radius of convergence within where I want to be. I don't know if that makes sense. We're not going to get too far into this, but if you're saying, well, what the hell is the use of this if you can only look in that interval? Well, that's what the great thing about Taylor series is, that you can move that interval around so that you wherever you're interested in looking, you move it to that spot, and that's where you can approximate. Okay, let me look at something real quick. What number was that? 14? Who has my answers for this chapter, for this section? I don't think I gave anyone the answers yet, did I? Yeah. Was that this is the answers. I've never done that problem, so I just want to make sure I didn't do anything wrong. This is what we got, right? It's x plus 3 to the n, and 3 to the n plus 1, there was a -1. The radius of convergence was 3, and we had that? Okay. Good. Now, does everyone have a book or not? Does everyone at least one book at each table? Yay or nay? You got a book back there? Go to page 484. 484? Yes? Table 1 on page 484. You are allowed to have that on your final. I will make a copy. I will provide it for you. Okay? But I want you to know you'll have it. What it is it's common common Maclaurin series. So look at the one Sine x. We just did, well, I did it, I handed it out, it was done on this page for you, right? Then we did cosine, didn't we? And that was the formula we had, wasn't it? -1 to the n, x to the 2n over 2n factorial. right? And then if these are other common functions in their Maclaurin series. And what we'll do is we will use these to find Maclaurin series for even more complicated functions, which is what I'm about to do. Okay? So on a test, on the final, if I say, find the Maclaurin series for cosine using the definition, that means you have to find all the derivatives and plug in all the values. If I say find the Maclaurin series and I don't tell you to use the definition, you can use this table, which means you don't have to do all the work. Make sense? Okay, here's the next example. I'd like us to find the integral, the antiderivative of e to the negative x squared dx as an infinite series. Now, the antiderivative of e to the x squared is a very famous integral. You cannot determine that integral in a closed form. In other words, there's no technique of integration. There's nothing anyone's ever going to do to make that happen. Even Wolfram Alpha is not going to be able to get it. So the only way to do it is with an infinite series. So what I'm going to do first is I'm going to rewrite this integral. And, well, no, don't do the integral. I want to look at e to the negative x squared. Go to your table, and let's look at what the Maclaurin series is for e to the x. And if you don't like, or if it makes more sense to you, you can look at that x being a u, like it's a u, and then the formula off the table becomes e to the u equals sum n equals 0 to infinity of what? U to the n over n factorial, right? What do we have? What's u for us? Negative x squared, right? So if you write this in its Maclaurin series, it's sum n equals 0 to infinity of negative x squared in parentheses to the n over n factorial. Do y'all remember how to find the antiderivative of a series? We did it last class. You find the antiderivative? There's a formula for it. But before we can do it, we have to split it up. Look, the formula, the notes from last class, it's the page that said theorem, term by term, differentiation and integration. At the bottom, there was two formulas. It said other ways of saying this. Remember that? Before I can use that formula, I must look at this series, the Maclaurin series, and I must get it to look like a c sub n times x minus a to the n. So watch me mess with this. Okay, this is the same as negative 1 times x squared to the n. I'm going a little slower, but yes, I agree with you. Over n factorial. I'm making sure you understand that that negative in front of the x squared is not getting squared, right? So it's a negative 1 by itself. Now apply the nth power to each of those. Negative 1 to the n, x to the what? 2n, all over n factorial. Now the negative 1 to the n over n factorial, that's your c sub n. The rest of it is your x minus a to the n. So we'll just do a power rule on the x to the 2n for integration. Y'all ready for this? I'm going to go back to the original problem now. the integral of e to the negative x squared dx should be equal to the integral of the power series, sum n equals 0 to infinity, negative 1 to the n over n factorial x to the 2n dx. So there's my power series. You're trying to get x by itself, just x as a base. So it looks like an x minus 0, right? This right here is like an x minus 0. That's what you're going for. A is 0, yes. And that means that you had to peel that negative off of it. Because then it wouldn't be x minus 0, it would have been negative x minus 0. You need to be positive x. Does that answer your question? Okay. All right, so what should the antiderivative be? A constant plus sum, n equals 0 to infinity. What happens to c sub n? Stays the same. Negative 1 to the n over n factorial. And then now the antiderivative of x to a power is 1 over 1 plus that power, x to that power plus 1. So it should look like 1 over 2n plus 1, x to the 2n plus 1. You did derivative, yeah. That's it. And you could write terms out, couldn't you, of that? You could now write some terms out. Should we or no? Yeah, we can write a few. Let's see. This is c plus, let's let n be 0. X, do you get x? If n is 0. Then minus, if n is 1, we get 1/3 x cubed. Yeah? If n is 1. Then plus, now n is 2. 2 factorial. So 2, and then I'm going to have 5. So 2 times 5, x to the 5th. Then minus 1 over 2 times 3 times 7, x to the 7th, plus dot, dot, dot. I'm starting to get the pattern there. That should be it. Questions?
So when you take the integral of a sum, it's going to always be the sum, right? And then you're just going to integrate the x.
Yeah, I'd like to show you what we actually did here. Let me show you something. When we had earlier, when we had e to the negative x squared, and we rewrote that as sum n equals 0 to infinity negative x squared to the n over n factorial, right? That's what we had earlier. Let's just write down what that is. Let's let n be 0. If n is 0, what do you get? 1. Okay, if n is 1, negative x squared, right? If n is now 2, x to the 4th over 2. Next one, minus x to the 6th over 3 times 2, right? Let's do one more. Plus x to the 8th over 4 times 3 times 2. Understand? Now, integrate that. Each of those, one at a time. Take the antiderivative. What's the antiderivative of x? I mean, sorry. of 1. No, antiderivative. X. Okay, antiderivative of x squared, 1/3 x cubed. Antiderivative of x to the 4th over 2, 1/10, but it would actually be 1 over 2 times 5 x to the 5th, and then the next one would be 1 over 2 times 3 times 7 x to the 7th, and so on and so forth. Isn't that what we just got? We just got that, didn't we? So either way, and you should be proficient at both. Write out the series, integrate term by term, or write out the series, integrate the series, write out term by term. See the two different ways to get to the same result. Plus a constant, right? This keeps going if we integrated this. If we integrated that. Yes. So that infinite series. And then if you wanted to put limits of integration, you could. And then all you do is plug those two, like if you want to go from like 0 to 2. You plug in 2 to this. That would be one number, and then you plug in 0, and then subtract the two answers. That's your area. Make sense? Okay. All right, moving along here. Damn, it's already 10 after. All right, multiplying power series. Okay, I'd like for us to find. Let's try for 4 terms of the Maclaurin series of f of x equals e to the x arctangent x. So let's, again, flip to that table that you have, page 484, and notice that we have Maclaurin series for both e to the x and the arctan, right? We have series for each. So I'm going to rewrite this as equal to, first, the series for e to the x, which is sum n equals 0 to infinity x to the n over n factorial, times the arctan, which is sum n equals 0 to infinity -1 to the n x to the 2n plus 1 over 2n plus 1. Arctan, not on arctan. Do y'all see that's right off the table here? Right off the formulas? Now, we are multiplying these, right? So it's this one times this one. Unfortunately for us, and I think this was a question that was posed from that table at some point in time, is that if you have a product of 2 series, can you make it a series and the product inside? And the answer was no. You can't just throw these together. In other words, you can't just make this a new sum and put this one right next to this one inside a single sum. It won't work. So what we're left with is trying to figure it out mechanically. So what I'd like to do now is I'd like to write out e to the x, which is this. Just write out the first few terms, right? So the first few terms of e to the x are going to be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 forever, right? That's e to the x. And then what are the first few terms of arctan? X minus x cubed over 3, x to the 5th over 5 minus x to the 7th over 7 plus dot, dot, dot. And now we need to multiply these two together. So how do you multiply polynomials like this? First term here goes to everything over there. Then second term, everything over there. Third term, everything over there. Fourth term, and that's the way you do it, right? So that's the way I'm going to do it. Now I'm going to have to at some point wave my hands because I can't do 1 times everything because I could be there forever. So I'm just going to go 1 times a few of those, then that next one, and I'm going to start listing them out. So I have 1 times all of these, which equals the same thing. I'm going to go to a smaller pin here. X minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot, 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 plus, now let's go to the next multiplication, which would give me what? My next multiplication through is this one. That's just an x, right? So it's going to give me x squared minus x to the 4th over 3 plus x to the 6th over 5 minus x to the 8th over 7 plus dot, dot, dot. And then I go to the next one, which is a pain in the butt, to say the least. Okay, that's x squared over 2, right? So it's going to become x cubed over 2 minus 5th over 6 plus 7th over 10, right? X to the 9th over 14, la, 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 right? One more. The next one that we multiply through is x cubed over 6, right? Through to all of those. So let's do that last one. I know we're all already exhausted from this. So we have, I'll do it in black, I guess. Or I haven't used green. I'm going to just put it below this. Plus, what was it? X to the 4th over 6 minus x to the 6th over 18 plus x to the 8th over 30 minus last one, x to the 10th over 7 times 6, 42, right? Dot, dot, dot. Now I want the first 4 terms. So the first 4 terms would mean from lowest power of x down. So what's the lowest power of x I have? X by itself. So this equals x. Now, x squareds. Do I have any x squareds? I have 1x squared, so plus x squared. I've got 2 of the 4 terms. Now x cubed. I have x cubed here, x cubed here. So what's negative x cubed over 3 plus x cubed over 2? It'll be over 6. Let me write it down. I'll go one more. Look, I'm trying to do negative x cubed over 3 plus x cubed over 2. So x cubed over 6. Okay, but the next one now, what would our next one be? X to the 4th. We have an x to the 4th here, and an x to the 4th here, which would be negative, well, you can do a common of 2. I'm going to write it down so everyone knows what I'm doing first. And then I'm just going to go plus dot, 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 because that's going to give me the first 4 terms, right? Okay, so we get x plus x squared. What did we say this was? Plus x to the 3rd over 6, and then minus x 4th over 6, plus forever. Those are the first 4 terms of, do y'all see how that worked or not? Any questions? What's wrong? 4 terms of the power series. Yes, of the Maclaurin series. Well, these are the terms of our series. I already did. Well, I'm not sure what you mean substitute a sub 1. I took 2 functions that I know the Maclaurin series for, wrote them as their series, wrote them out term by term, dot, 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 multiplied out, got this thing, and started collecting like terms together, starting with the lowest power of x down, like lowest power of x up. And I stopped when I got to the 4th term. Not the 4th power of x, just the 4th term. So I have an x term, an x squared term, an x cubed term, and x to the 4th term. I don't have any constants, do I? No. Now this keeps going forever. So if you wanted to approximate now, what is f of 2? You'd be looking at the series that we got below as its approximation. Start plugging 2 into that, go out as far as you need to go to get within the accuracy you want. Now, what would the radius of convergence be, though? Look back at your table. What's the radius of convergence for e to the x? For e to the x. Infinity, what's the radius of convergence for arctan? 1. So when you multiply 2 together, the radius of convergence would be 1. Because arctangent would be restricting our radius to 1. Smaller, yeah. So we could only plug certain values in to this. But again, we could shift it by doing a Taylor series. Well, smaller is kind of weird when you talk about intervals, so it would be their intersection, yeah, where they overlap. All right, let's now look at our last, I think this is our last example. Yes. Shit. Okay, let's look at All right, let's do Maclaurin series. Find the Maclaurin for f of x equals tangent x. Or you know what? Let's do some. I've already done tangent. Let's do, I've never done this one before. Cosecant x. So you go to your table. Does your table have cosecant x on it? Oh, shit. But what is cosecant? 1 over sine x, right? Now, does your table have sine x? Yes. So this is really 1 over the infinite series, power series, what's sine? -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. That division bar goes all the way across. I'm glad you asked that. Can you just flip that? Can you just put the sum on top and flip everything on the bottom? No. Think about it this way. If I have 1 over 2 plus 3 plus 4, right? Or, yeah, you know, do it this way. If I have 1 over 2 plus 3 over 4 plus 5 over 6, does that mean just flip them all and make it 2 over 1, 4 over 3, 6 over 5? No. And that's what you would be doing if you tried flipping that fraction, the series. You'd be trying to flip it, but you can't. You have to convince yourself that's true, but it doesn't work. So what we're left with then is, well, 1 divided by the infinite series. So let's write out the terms of the infinite series. They are x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus like that, right? You agree with that? Now, how do you divide? And I'm going to leave this for you. That's right. This is that horrible teacher's problem. How do you get from that line to the next line? Just divide 1. That's the problem right there. Yeah. Yeah. Since r is in for radius of convergence, all the radius convergence tells you is what values of x can you plug in there and this formula will work. It doesn't say that becomes infinite. It has nothing to do with that. It just says, can you plug 2 into that? Yes. Can you plug 10? Yes. Can you plug 1,000,000? Yes. Why? Because the radius of convergence says I can plug anything I want into that series and it's valid. Think you can handle that? Yeah. Let's make it a quiz. Take-home quiz? Sound fair? See if you can do that? Yeah, you got a whole week. See if you can. No, Thanksgiving. Let me see something real quick. Where's my... Trying to find... I did that video. I don't remember where I put it. Yeah. Yeah, but I did it right here. Hold on a second. Trying to think of a way I can give you a hint because it's not as clean as this one was. This was the problem that that horrible teacher had. But look at, now that you see it, this is not so far-fetched anymore, is it? This is an infinite series, 1 divided by that, right? So something you may run into at some point in time. Well, ours, look at when you do this part in yellow, you do the 1 in the division box and you put the denominator out here. Then you start saying, okay, what do I multiply 1 by to get 1? And we put a 1 here, right? That's the way it would start to work. What's wrong with ours, though? It starts at x, doesn't it? That's right. You could factor an x out. You could take an x out of everything. Just like imagine this. If that x cubed was in here, that'd be x cubed, right? And then you wouldn't be able to do x cubed into 1. But by pulling an x cubed out, you can get the 1 in 1 to work. So what you would have for your problem is you're going to need to somehow pull something out first, then do all your work, and then come back through with that x. Whatever you get here. Yeah. So like for this right here, well, remember, it comes out of the bottom, though. Right? So if this yellow part turns into this, you're now going to come through with a what? A 1 over x cubed through each term. We'll see how many people can get that, figure that out by next class. Not this. I already did that. But that video's on my YouTube. It's not on our Calculus 2 playlist, right? Somewhere else, some miscellaneous or something. If you go, I go through that whole computation in that video. That'll help you. Unless you have a different way. I mean, it's taught different ways in different countries, but if, you know, long division, the way we know it here, that's the long division. No, I mean, there is, right? I mean, there's different ways of division. Yeah, you have a different way, yeah. We're going to make it a quiz. We need another quiz. It's a take-home quiz, so see how you do with it. Finish that out right there. Okay? There's something wrong? Where? For which one? This one? Oh, there was something wrong I did? Oh, well, let's talk about that later then. Yeah, I'll keep it right there. We can talk about it after class. Okay. Homework for this section. Yeah. For 8.7, this is page 487 is where it starts. Okay, Maclaurin series. So I need you to be able to find the Maclaurin series for a few functions. We've already done sine. I think number 5 is a good one. I think 13 is good. I didn't post the notes from last class? Should we can prove who's right now. I'm pretty sure she's right because I put them out there. But I'll look. Hold on. Okay, let me see. Use the Maclaurin series from a table to find, let's see, 31. I like 32, even though it's even. Should be good. How about just one integral, 43? That'll be it. Keep it right there. Now, I want you to think about something. I know we only have 8 minutes, but I want to start thinking about the next chapter. Just plant the seed, because we have a whole week before we see each other again. And I don't have any more videos from last spring over anything I covered from chapter 9. So I want you to start thinking about this. I put together a real quick little thing for us to look at. You know what? Yeah, so just sit back. You don't need to take notes or anything right now. All right, and what I'll do is I'll start this out by talking about the classic idea of what a function is to us, right? For us, a function has always meant input-output, right? For us, a function f, you have an in, it goes to an out, right? One number in, one number out. And to be a function, you had to only have one output, right? Like you couldn't plug in x and get two things come out. Right? So your picture could not be this. You plug in the number x and it goes to two values, right? Whatever they were, two different numbers. That would fail the vertical line test, all right? So this is a function, right? No problem. If I change the values of x, this is x squared is the equation. If I pick a value of x, I can determine what y is. So if I slide my x around, my y changes. And this is a table of some x values and some y values. X goes in, y comes out. Yes? Now what I want you to do is look at what we've always considered to be a circle, right? I mean, just think about a circle for a second. Is this a function of x? No, because if I pick a value of x, let's say somewhere around here, x, there's actually one y value up here, and there's another one down here. And the reason why is because a circle, unit circle, we'll say this is unit circle, comes off that equation x squared plus y squared is 1. So if I solve for y, I have to take a square root, which gives me plus or minus, right? So I get that. So that means I plug in an x. Like let's say plug in 0 for x. It spits out positive and negative 1. So if x is 0, I'm up at the top and at the bottom. What if x is 1? I get 0. So that works, right? What if x is negative 1? Well, that works. There's only one answer. But if it's anything between negative 1 and 1, I have two answers. Agreed? So this does not follow what we consider to be a function. So the way we've gotten around it in the past is to say, oh, then we look at it as two functions, the top one and the bottom one separately, right? That's the way we've done it. But there's another way, and that's what we're going to look at. So I want you to look at this instead. Here's the parabola we just drew a second ago. And what I'm going to say is, and we've talked about this, I know we have because we did this on our calculators before, parametric mode on your calculator. Instead of saying that y is equal to x squared, we're going to let there be a parameter, which we'll call t, which is the clock that's going to start. We're going to let t go between negative 2 and 2. We're going to let x be equal to whatever t is, and we're going to let y be equal to t squared. So what we have instead now is the clock running in the back, and then the x and the y coordinates are dependent upon that clock. But it draws the same exact picture, doesn't it? If I let my t vary, my x's and y's change exactly the same as they did in the previous parabola. Y'all see the difference? I mean, they look exactly the same. Picture-wise, they're exactly the same. But the way I defined it is different. Now let me show you why this is important. If I define these two equations, x is cosine t and y is sine t, then what I can do is if I let my t go between 0 and 2 pi, I can change my clock, change my x and y values, and I can draw a circle. But why is this still a function? Look at it. I'm going to start letting my t start. Okay, look at where I am, up at that point right there, right? Come around. Look at the point up on top. Why is this point now different than this? Why do we not have a vertical line test anymore? In terms of t, see, because what is the t that gets you that point? Pi over 2. So I plug in pi over 2, it spits out that point. In the previous thing that I did a second ago, when we plugged in 0, it spit out 1 and -1, right? Now when I plug in pi over 2, it spits out the 1 on top. And how do I get the 1 on bottom? I just go around a little more. And I plug in 3 pi over 2, and I get this one. So those 2 points come from completely different places. Do y'all see that? What goes into the function, one of them gives you this, one of them gives you this. Okay, so what about this then? I need to change something in my code real quick. Why didn't it like that? So there's my circle, right? So what about there? I'm at the top of the circle, right? I keep letting t go around, t go around, t go around, and now I'm back there. So now have I violated being a function? Why not? What's that? The whole rule for a function is that one input has to go to one output, right? You can't have one input go to 2 different places. So I'm on top of the same thing I just was, right? But look at my t. It's different than it was before too. So I have a different t, and I'm at the same place. It's still a function. I can draw circles on top of circles on top of circles forever, and it's still a well-defined function. For every input, there's an output. And this becomes great later. I'm out of time. Because a lot of things in the real world, like in 2-dimensional space, they don't behave like functions. They don't move around and say, oh, but I must follow the vertical line test so that I can do calculus on it. Right? It does what it wants to do. All right. Everyone have a good Thanksgiving. Do your homework. See you later.